Hello everyone, welcome to Physics 225. This is your lecture 20. Next week we have no lectures. You'll have fall break, or aka Thanksgiving break, your turkey break. Also, you have one homework due tomorrow, and then next week there's no homework due. Today's quiz was covered on linear momentum. Okay, that was chapter 9. Okay, so we are on schedule, right? So next week there's no class. So after that we'll finish rotational motion. So in terms of rotational motion, we started with angular acceleration Monday, right? So alpha, okay, angular acceleration, which is change in angular velocity. Okay, this is a vector quantity. So for you to find the direction of angular velocity or acceleration, you will have to use the right-hand rule. Okay, I have shown you some pictures in the last lecture. Make sure you go over that to learn the right-hand rule. So if you have a uniform circular motion, in that case, your net acceleration is pointing towards the center. Velocity is tangential. Tangential velocity equals to r times omega, where magnitude of acceleration is v squared over r, which v is r times omega, so you can get r omega squared. So in terms of non-uniform circular motion, okay, you have acceleration centripetal and acceleration tangential. In this case, your acceleration is not the net acceleration is not directed towards the center. Okay, it's the vector sum of acceleration tangential and acceleration centripetal. Okay, so as mentioned last week, okay, there's similarities between the equation of linear and angular angular kinematics. Okay, so only thing is you have to be careful with your variable. So in this case, x is translated to theta. Yeah, v is translated to omega, a is translated to alpha in terms of rotational. Okay, so the next one is moment of inertia. Okay, when we talk about mass, okay, mass determines how hard it is for object to move. Okay, moment of inertia determines how hard it is to rotate an object. Okay, when we talk about rotational inertia, if the mass is distributed far away from the center, it's harder to rotate. If you're at the gym, if you take a barbell and a dumbbell of the uh, same mass, okay, so let's say you have same weight, let's say like 50 pound, let's not go 50, let's go say 20-pound barbell versus 20-pound dumbbell. If you try to rotate it vertically, it's harder to rotate a barbell because mass is distributed far away from the center. So in this case, inertia is given as mi/ri squared. So this is, let's consider, let's say particle 1 here, 2, 3, 4. This is r1, r2, r3, r4. So I is mi/ri plus m2r2 for same thing in here. Okay, same thing would happen here. Since r is greater, the radius from the center is, the distance from the center is greater, so this system will have the higher inertia. So inertia depends on the object, okay, on the shape of the object. For example, inertia for a disk is 1/2 mr squared. Inertia for a solid sphere is 2/5 mr squared. Okay. So if we know the moment of inertia rotating through the center, we can find the moment of inertia if it's rotating through any other point. Okay, and for that we use the parallel axis theorem. Okay, I would be you have to know the inertia center of mass, and then you need to know how far away from the center it has been shifted. So in this case, we have an object where center of mass is located at this point. Oh, sure. Did my, yes.